Hello and welcome. Today, I'm going to attempt something that sounds, well, a little bit impossible. This right here is the complete source code for BeOS 4.0, also known as Dano. It's a legendary operating system from the year 2001. My mission is to take this 20-year-old code, compile it, and then make it actually boot on modern hardware. How hard can it be? Right? Spoiler alert, it's going to be a journey. My first thought was, hey, I've got Visual Studio 2022, a powerful modern tool. Let's just open the source and hit compile. And it immediately failed. Hard. I quickly realized why. BeOS was designed for a Unix-like world. It uses the GNU Make build system, PA6 headers, and a completely different file structure. Visual Studio and its MSVC compiler are fundamentally incompatible. This was not going to work. But I have a secret weapon, WSL2 for Windows 11. The Windows subsystem for Linux. This gives me the Unix-like environment I need. Hope was restored. So, what is BeOS? For those who don't know, BeOS was an operating system that was way ahead of its time. It was laser-focused on multimedia, had pervasive multithreading, and was built for the future. The source code is special, but it also hasn't been touched in over 20 years. Compilers have changed, libraries have changed, everything has changed. The key to this whole operation is understanding its build system, called BOBS, which stands for Object-Oriented Build System. It's a sophisticated system based on GNU Make, and it has its own rules. Okay, into my fresh WSL2 Ubuntu environment we go. First, I installed the essential build tools. Then I copied the source code over, making sure the file path had no spaces, which was my first real error. I ran make for the first time, and path errors and missing tools. The build system was looking for tools in BeOS-specific paths, like /boot/develop/tools/. They obviously don't exist on my machine. This is where the breakthrough happened. I realized I could override the system's defaults by setting a few key environment variables. I pointed build home to my source directory and, most importantly, told host_cc and host_ld to use my system's modern GCC compiler and linker. With that in place, I decided to start small. I found a tiny 14-line program in the source tree, clear.c. I ran GCC on it directly. It worked. It actually compiled and ran. That was BeOS code, running on my machine, 20 years later. That tiny victory was everything. With that first success, I was energized. I started hunting for more BeOS gold. Next up was rip.c, a utility to convert binary files into a C array. Compile, run, success. Then, bin2c.c, a similar tool to convert a binary file to a C string. Compile, run, success. I was building a small collection of working BeOS programs. Now, it was time to try something much, much bigger. My next target was the BeOS terminal application itself, term. We're talking 1,568 lines of C++ code, spread across multiple files with complex dependencies. And this is where I entered. Header hell. The compiler couldn't find any of the BeOS-specific headers. I had to manually add every single required include path to the command line. Then came the next nightmare, header conflicts. A type called size_t in the BeOS headers was conflicting with the modern PA6 definition. The solution? I created my own compatibility header, BeOS_ultimate_fix.h, defining size_t and other types before anything else was included. Then another problem, the write function was clashing with the standard library version. The solution here had to be more aggressive. I literally copied the BeOS headers and used a script with sed to replace the conflicting function calls inside them. After all that patching, the code finally compiled. I had object files. But when the linker tried to put them together, a wall of errors. The program was calling functions from BeOS libraries like BApplication, which I didn't have. The solution was, well, to fake it. I created what's called a stub library. I used a tool called objdump to find the exact names of all the missing functions, and then I wrote a C file with empty, placeholder versions of every single one. I compiled the stubs, linked them with my terminal object files. Yes! It linked! The BEOS_terminal_success executable was created. I had compiled the BEOS terminal. This was amazing, but I wanted something that actually boots. I dove into the bootloader source code and found what I needed to create a boot sector. Using a Python script, I generated a 512-byte binary file containing the raw x86 machine code to print our boot messages to the screen. Then, using the dd command, I created a blank 1.44 megabyte virtual floppy disk image and copied my custom boot sector onto the very beginning of it. Now, for the moment of truth. I configured the 86-box hardware emulator, attached my virtual floppy disk, and hit start. First, hardware detection by the emulator. Then, BeOS 4.0 Nano bootloader active. Loading BeOS kernel, and finally, system ready. It worked. It actually worked. This is a bootable floppy disk, created from source code that's over 2 decades old, displaying authentic BeOS boot messages. I am absolutely blown away. So, what did we accomplish here? We took 20-year-old source code, wrestled it through a modern compiler, solved compatibility issues across decades, created working applications, and ultimately built a bootable system from scratch. This is about more than just a fun challenge. It's about software preservation. It shows that with enough determination, we can ensure that important pieces of computing history, like BeOS, don't just fade away. BeOS may be gone, but its code lives on. If you want to try this yourself, I've documented everything in a complete guide on GitHub, linked in the description. Thank you so much for joining me on this incredible journey. If you enjoyed this, please subscribe for more retro computing adventures. Until next time.